Hello, everyone. Welcome to this third series of videos related now to Chapter 12, three-phase systems. We're going to solve two exercises today. First one is problem 11. It says, if the source is balanced and VAN, which is the phase voltage, essentially this voltage, it's 100 plus 0J, meaning 110 angle 0. Calculate the following. A, express AN and BN in phase notation. Okay, determine V3, which is the voltage at the load Z3. Then determine P1, P2, and P3 given some impedances. So we have those three. We can calculate active power or real power consumed by each impedance. And then represent Z3 by a series connection of two elements. Okay, so let's go for it. So for this problem, first of all, we need to understand that this is a two-phase system. So we have two active sources, in this case denoted as VAN, and the other one should be VVN. However, the problem is kind of stating VNV, so that's kind of odd here, but it's how it's presented. So it's asking you to get VAN and VVN. So in this problem, we can say VAN is given. Okay, so 110 angle 0 volts. And of course, this is already, you should know this already. This is RMS value. So for VVN, we need to understand what's the property behind two-phase systems. So if we have one with angle 0, the other one it's going to be pointing the other way, right? So the angle is going to be 180 degrees apart. For a three-phase system, we have three phases. So the subdivision of angles is going to be 360 divided by the number of phases, right? So if n is 3, for example, then we're going to get 120 degrees separation between phases. That's exactly what happens for three-phase system, right? At 120 degrees apart. For a two-phase system, we have 360 divided by 2, that's 180. So that's 180. So we have phase A and phase B phasors. So what does it mean? It means that VAN is that, and BN, it's going to be minus VAN, or 110 angle 180. It can be plus 180 or minus 180. We're referring to the same phasor, right? So what does it mean? It means that this angle or this voltage is 110 angle 0, and this voltage Vn, this is B, this is N, right? B, N, this is A. It's gonna be 110 angle 180. Okay, that's the meaning of this. Of course, here it's referring to V and V, and these two are gonna be the same, right? Exactly what happens on problem 12 from your homework. Okay, so be consistent with this notation. AN, meaning A is the positive, N is the negative. BN, it's because B is the positive, N is the negative, for references. Okay, easy first problem. Second problem, determine V3. So what is V3? It's the voltage at the impedance Z3. So first of all, we need to calculate this this voltage. So let's call it V3, which in this case, if you notice, it corresponds with VAB. So what we need to do here is to calculate that voltage, and we can do that simply by stating a voltage law on this loop. So we can do easily VAN plus VNB equals BAB, which is equal to B3. Okay. So what we're doing here is this voltage. So we're following the loop, right? We have those three voltages and we're following this loop. So this voltage minus this voltage plus this voltage equals 0. And then we have our voltage voltage law. Let's make it even more explicit by Kirchhoff voltage law. Then we get that relationship. And then simply we're gonna say VAV or V3, which is what we want. It's gonna be VAN 110 angle 0 plus BNB, which is gonna be the negative of BVN, right? Let's remember this. Okay, BNB, simply the negative of BBN. Okay. So plus 110 angle 0, and we simply get 220 angle 0. So that's kind of the whole point of having a two-phase system. We can have one phase or monophase loads connected to 110, and just like Z1 and Z2, and we can have loads connected to the 220 outlet. Let's say AB is this 220. So that's exactly what happens on US household electrical systems. You have outlets that are the most common ones that run on 110, but you also have a face-to-face connection, which in this case corresponds to 220 volts. And the elements that consume more power are usually connected to that to those two terminals, just like a washing machine or a dryer are connected to these terminals, to twin. Okay, let's move on to the next one. It says determine P3, okay, determine P1, P2, and P3. So now we know the magnitudes and angles for each impedance, and now we can simply calculate power. So I would say, things going crazy. So what I would say the easiest way to go about, it's what I usually recommend. It's let's calculate current. We have voltage, we have impedance, then we simply identify what is going to be each thing. So why am I writing this down? Because we know that Z1 is connected to this voltage directly. So the current flowing through Z1, it's going to be the voltage at Z1 divided by the impedance, simply. Same with Z2. So what it's going to be, we can call it this current in that direction, that it's going to be this voltage, Vn, divided by the impedance, if we want to define that current in that direction. Z3, we have already V3, so V3 divided by the impedance is going to give us the current. So we already have all the things in place to define this. So 110 angle 0, the impedance for Z1 is, I believe is 50 plus 0J. So 50 plus J0. And that is going to give us 2.2 angle 0 amps. There we have current. Then let's call this I2. It's going to be, as we said, VN divided by Z2. This under the assumption that we're defining currents in this way, okay? This is going to be I1. This is going to be I2. And this is going to be I3, okay? That's our definition for directions of current. Okay, then this is going to give us EVN. We already have that, and that is 110, angle 0. Angle 180, we said, okay. 180 divided by Z2, which is 100 plus J45, okay? Again, here we can be a little different, and we could define the current this way. It would be completely fine. The only thing that is going to change is the angle. The module is still going to be the same. But we need to be consistent, basically. In this case, it doesn't matter. I use that definition, and let's keep with that. So let me calculate this. This is going to be 110 angle 180 divided by 100 plus 45J. That is going to give us in polar form 1 angle 155.77. Okay, amps. And finally, I3, it's going to be, we already did this, C3, that is actually, we said 220, angle 0, divided by 100 minus J90. Okay, that calculation is going to give us 1.64, angle 41.99 degrees amps. And now that we have voltage and current, real power, it's simple enough as this formula. P1, it's going to be the voltage at that element. So VAN, since we're not using the bar on top, we're referring to the magnitude times I1, magnitude again, times the power factor, or let's call it cosine of the angle of the voltage minus the angle of the current. So if we replace this, this is going to be, let's use numbers here, 110 times current I1, which is 2.2, times cosine of the angle of the voltage, 0 degrees, minus the voltage, sorry, the angle of the current, which in this case is also 0. Cosine of 0 is 0, and then we get our power, 242 watts. Okay, P2, it's going to be the same idea. The voltage at the load 2 times the current that we calculated times the cosine of the angle of the voltage minus the angle of the current. Voltage in this case is 110. I2 is, we calculated it's 1 times cosine of the angle of the voltage, 180 degrees, minus the angle of the current, 155.77 degrees. So one thing is important here is that you know that this is an inductive load, right? So for an inductive load, the current is always lagging the voltage. So the angle of the voltage is 180, the angle of the current is 155. So it's actually happening, right? The angle of the current, it's behind the voltage. So it's lagging. So everything makes sense. Yeah. If you're solving this problem and you're defining the current this way, you should get to the same conclusion. Okay. You should get to the same conclusion. So now we calculate this, and this should give you 100.3 watts. And finally, P3 is going to be V3 times I3 times cosine of the angle of the voltage minus the angle of the current. What is V3? It's 220 times I3. We just calculated 1.64 times cosine of the angle of the voltage, which is 0 degrees, minus the angle of the current, 41.99 degrees. And that is going to give us 268.17 watts. And that's how we calculate all powers. Now we go back to our initial problem. We have solved this one. And finally, we need to solve part 2. Part D, represent Z3 by a series connection of two elements. Okay, sounds kind of the lab activity. So in the lab activity, you don't have a series connection for part 2, right? You have a parallel connection. So the calculation for the lab is going to be a little different. However, this is simple enough that we can directly connect to what you're going to be doing in the lab. So D, so we know that C3, it's equal to 100 minus J90. So if this is an impedance with negative imaginary part, this equivalent must come from a capacitive circuit. That means that somehow this needs to come from some resistive part plus some reactive part, right? Which is the same as saying this is equal to R minus J over omega C. Whatever the R and C are going to be, okay? So for R, we can simply match real part with real part, right? Then we're going to say here real part R equals 100 ohms. The resistance does not depend on a frequency, so we're good at this point. Finally, for the imaginary part, then we get that 90 has to be equal to 1 over omega c, right? The minus j are already equal, so then we need to match the 90 with the 1 over omega c on the other side. So now frequency, it's very important. So here we can define C equals 1 over omega, which is 2 pi f times 90. So what's the frequency that it's defined for this problem is 60, actually, the same frequency of the grid, right? 60 hertz. So that means that f is simply 60, and you solve this, and you should get 29.47 microfarads. That's it. Again, the same way would apply for any other load. For example, Z2. Z2, it's a real part plus a real imaginary part. So this thing must come from an R plus J omega L circuit. Must come from that. Okay. Okay, I think that concludes this problem. I hope it's helpful. See you on the next one.